Hi, I'm Saranga Komanduri, and I'll be presenting this paper on behalf of my co-authors, Richard Shay and Lorrie Cranor from Carnegie Mellon, and Cormac Herley, who just spoke, and Stuart Schechter, who will be speaking after me from Microsoft Research. So 20 minutes is not a lot of time, so I'm going to talk fast. But if you have a question and you don't get a chance to ask, feel free to talk to me or any of my co-authors after the session, or send me an email. Okay, so there are three actors that we can consider in the authentication ecosystem. There are users who create passwords, adversaries who want to impersonate users, and system administrators who try to block adversaries and protect users' passwords. So what do system administrators do to protect users? There are many things that they can do, but one of the tools they have is password policy. Policies constrain users' passwords. For example, a policy might specify that passwords must contain a number or a symbol or an uppercase letter. Such character requirements are a common component of password policies. They mandate a minimum length or a minimum number of various character classes. However, simple character requirements don't work very well to improve security. In a study we recently presented at CHI this year, these were the most common passwords in a policy that mandated 3 different character classes and a minimum length of 12. This is important because the default password policy on many systems only uses character requirements. In Microsoft Active Directory, the default policy requires 3 out of 4 possible character classes and an 8-character minimum. We call this policy 3-class-8 in the paper, and find that the 3-class requirement has almost no effect on security. At the same time, this requirement makes passwords harder to type, especially on mobile devices. So in this work, we focus on the security of the weakest passwords using an online attack threat model. In an online attack, the attacker has a limited number of guesses, say under 100 or even under 1,000,000. The goal of a password policy under this model is to make the weakest passwords across an organization harder to guess on the assumption that an attacker could use any user's account as a beachhead for further attacks. In our paper, we confirm that certain sets of character requirements are insufficient for preventing weak passwords. We also introduce a system called Telepathwords, which detects weak passwords using a guessability model while providing real-time feedback. And we show that real-time feedback, when coupled with a mechanism for preventing common patterns, can produce a policy that is both significantly better in terms of security than character requirements, but not significantly different in terms of usability once passwords have been created. So this is the Telepathwords system. As the password is entered, Telepathwords provides predictions for what character the user is likely to type next. This is similar to autocomplete, except that users are discouraged from typing the predicted characters. One of the goals of Telepathwords is not just to detect weak passwords, but to communicate to users why a password is weak. We believe that by showing users that a machine can guess their password, they will understand that an attacker could also. To help users understand this, the predictions are accompanied by short explanations which provide the predicted characters in context. The guesses can also be turned off for security against shoulder surfing, and the feedback bar above the password field provides users with a scoring history. Characters which are one of the 3 predicted characters or are commonly substituted for those characters get a red X. Unpredicted characters get a green check mark. And a Telepathwords-based policy requires some minimum number of unpredicted characters, but has no other requirements. Password policies actually haven't changed much in the last 35 years since character requirements were introduced by Robert Morris and Ken Thompson. They proposed a 6-character minimum requirement in 1979, and 33 years later, Joe Bono found that a 6-character minimum, even when accompanied by a graphical password strength meter, did very little to improve security over no requirement. Many websites provide password meters to prevent users from making weak passwords, but password meters are typically based on character requirements. Even worse, de Carnegie and Mellon surveyed password meters across several websites in 2013 and found that meters are very inconsistent. They found that in many cases, passwords were judged strong on some sites and weak on others. To address these issues, Wheeler introduced a very sophisticated open source meter called ZXCVBN, which estimates the entropy of passwords using heuristics and catches many common patterns. In contrast with these password meters, one of our design goals with Telepathwords is to help users understand what makes passwords weak and provide actionable feedback about how they could be made stronger. So the architecture of Telepathwords employs multiple weighted predictors that each produce guesses for the next character along with likelihood scores. For example, we have a predictor that takes the input string and completes it using an n-gram model based on a corpus of search queries. In this case, show me the is most often followed by money in the n-gram model, which leads to M as the next predicted character. The n-gram model also includes the RockU password set and could include other password sets. Each predictor can transform the input string, so we can undo common substitutions like converting letters to symbols and then look up the transformed string in the n-gram model. When we detect this, we can alert the user that these behaviors do little to increase the strength of their password. We also employ other predictive models besides the n-gram models. Here you can see a keyboard pattern. Patterns such as these are quite common in passwords, and modern password cracking tools will actually generate these patterns. So since they are common, shorter patterns will get picked up by the n-gram model built from passwords. So here you can see that ZAQW was found in the corpus, and the as-in explanation provides entries from the corpus that match the current string. But as the pattern gets longer, it's not found in the corpus, but is found by our general pattern predictor. We have another general predictor for repeating patterns, and one for interleaving strings. Multiple scores are summed together across all of the predictors for each character to obtain the final list of most likely next characters. The key idea here is that we can easily extend the system with more predictors to cover more behaviors as desired. And I also want to note that there are many ways that one could implement this sort of system. Ours is just one example and certainly not the best possible implementation. Next, I'll go over our evaluation of Telepathwords as part of a randomized controlled user study. The site was deployed to the public in December of 2013 and was reported on a few tech blogs and news sites. This let us know that the system could operate at scale, and it served almost 60,000 sessions per day in the first week. After that, traffic dropped off to under 1,000 sessions per day. In February, we conducted a user study on Mechanical Turk using a study website hosted at CMU. We used Telepathwords transparently using its JavaScript API. Participants created passwords under 6 policy conditions, of which 2 were Telepathwords conditions. Since Telepathwords provides real-time feedback, we included some form of visual feedback in each condition. Our control condition was basic 8, which required a minimum of 8 characters but had no other requirements. In all of our conditions, the visual feedback was shown above the password field. This is how the feedback changed as the password was entered. All of our conditions also had a show password box, and clicking this box was completely optional for participants. The next condition is 3 class 8, which adds character requirements to basic 8. These passwords must contain at least 3 different character classes, where the classes are lowercase, uppercase, digit, and symbol. This is our baseline condition to which other conditions will be compared and is the default policy in Microsoft Active Directory. 3 class 8D adds a dictionary check to 3 class 8. This check removes non-letters from the password and checks the resulting string against a dictionary that was built for password cracking. The dictionary has about 3 million entries. Here you can see an example password in this policy. In contrast, 3 class 12 increases the length requirement of 3 class 8, requiring a total of 12 characters, but doesn't impose any further requirements. Finally, we tested 2 Telepathwords conditions called Telepath and Telepath V. In both conditions, the only requirement is that the password have at least 6 unpredicted characters. In the Telepath V condition, the Show Password button is checked by default, allowing users to see their passwords as they type them. We found no significant difference between Telepath and Telepath V on any metrics. So to summarize our conditions, we have basic 8 and 3 class policies that incorporate traditional character requirements, and also policies that I will call dictionary policies because they check passwords against some sort of dictionary. We collected passwords from a little over 400 participants per condition. Demographics were typical for MTurk with a median age of 27 and the study limited to those 18 and over. 60% were male and 44% reported having a bachelor's degree or higher. And we restricted the task on MTurk to those with a 95% acceptance rate and a location within the United States. After they consented to our study and before creating their passwords, participants were told to imagine that their primary email account had been compromised and their email provider was implementing a new password policy. We didn't just ask participants to create a password, we also asked participants to take a survey and then recall the password, and we only used passwords from participants who stayed to reach the end of the first day of the study. 2 days later, we contacted participants through MTurk and asked them to return and recall their passwords again. Next, I'll describe our metrics. For security, we have 2 main metrics. The first is a guessability measure we call WEIR+. This is a refinement of the guessing algorithm from Weir et al. And is described in more detail in the paper. We can use this algorithm to measure the number of guesses needed to find the weakest single password in our sample, and then to guess 2.5%, 5%, and 10% of our samples. We also use entropy estimates provided by the ZXCVBN project that I mentioned earlier. This gives us an entropy estimate for each password that we can use to figure out the minimum entropy of a password in each sample, or compute other measures over the distribution of entropy values, like percentiles. We would have liked to use a probability metric, but even with over 400 passwords per condition, all of the passwords we collected were unique within each condition, so there was no way for us to estimate probabilities in any meaningful way. We also had a number of usability metrics, but in this talk, I'll present creation difficulty, whether participants found the visual feedback insightful, and how hard the resulting passwords were to recall 2 to 5 days after starting the study. So here's a graph showing the strength of the basic 8 condition under the ZXCVBN metric. So this graph is an ECDF curve on entropy scores. So for a given entropy score on the x-axis, say 5 bits, the y-axis shows the percentage of passwords in the sample with a score equal to or lower than the given score. In this case, a little over 1% of passwords have an estimated entropy of 5 bits or less. And 10% of passwords in Basic 8 have an estimated entropy of 15.5 bits or less. The weakest password is the one with the lowest or minimum entropy, and you can find it in the lower left corner of the curve. Here are the curves for all 6 conditions. Curves that are closer to the right side of the graph are better because they have higher entropy scores for a given percentage of passwords. The dictionary policies shown here have the best minimum entropy of the policies we tested and are the strongest policies overall. Their curves are consistently to the right of the other conditions. The policies roughly cluster into 3 groups, with Telepathwords conditions performing best, followed by the 3 class 8D and 3 class 12 conditions, and finally the basic 8 and 3 class 8 conditions. As you can see, these last 2 lines are pretty close. So under this metric, the 3 class character requirement appears to provide almost no improvement in security over just a basic 8 requirement. And this is a graph using our other security metric, the WEIR+ guessing algorithm. To compute guess numbers here, the WEIR+ algorithm was trained separately for each policy. Again, the weakest passwords were found in the character requirement only conditions. As expected, we have password and password 1 with a capital P for the basic 8 and 3 class 8 conditions, but we also have ASDFGHJKL123 for 3 class 12. This was the 87th guess made by our algorithm. The dictionary policies fared much better, where the weakest passwords were Pokemon 91 for 3 Class 8D, which was around the 65,000th guess, and I am a believer and 1024 Scott for the Telepath policies, and these required close to 1 million guesses. Beyond the weakest passwords, the dictionary policies were once again stronger than the character requirement only policies, up to very large numbers of guesses. Once again, we find no substantial difference between Basic 8 and 3 Class 8. On the usability side, the differences in recall among those who returned after 2 to 5 days were not significant between conditions. And here are percentages for each condition with 95% confidence intervals. However, the condition did have a significant effect on creation time, which is the amount of time spent by participants to create their passwords. Here are the median times per condition. The Telepathwords conditions took much longer, about 90 seconds, compared to 30 to 50 seconds for the other conditions. However, Telepathwords was a novel condition with instructions and an interface that users probably hadn't seen before, so this might account for some of the extra time. Users also felt that the password creation process was more difficult and more annoying with Telepathwords than with the other conditions. However, when asked whether the visual feedback gave them insight into the strength of their passwords, 75% of participants in the Telepathwords conditions agreed that it did, compared with 35 to 60% in the other conditions. In conclusion, we found that real-time feedback can help users under dictionary policies avoid weak passwords. And this comes with a usability cost on creation in terms of time spent and annoyance. But on the plus side, users felt that the feedback provided by the Telepathwords system gave them insight into the strength of their passwords. We also found that character class requirements alone had little to no effect on security using our metrics, which focused on the guessability of the weakest passwords. Dictionary policies such as Telepathwords were substantially better at preventing weak passwords. And that concludes my talk. Thank you very much.
Questions?
Stuart from Shay Security. I have a question. Since I think the main burden for the user to create strong passwords is that they have difficult time to memorizing all the passwords. So for Telepath, it helps the user to create those strong passwords, but still have a difficult time to memorizing all of them. So my question is, compared with some random password generator, what's the advantage of the real-time feedback approach? Thank you.
Yeah, right. So the question is, Telepathwords will help users make stronger passwords, but they might be much harder to remember. So in our user study, we tested recall after 2 to 5 days, and we didn't find any significant difference between conditions in terms of how much difficulty users had recalling them, giving them 5 tries. Sorry. So we have done previous experiments at CMU where we've done randomly assigned passphrases, and we found that in those conditions, users find them much, much harder to remember than passwords that users create on their own. So I think one reason for the difference between the results in this study and the results from, say, a randomly assigned study is that in this study, we're trying to just prevent the weakest passwords in a sample from being created. And this doesn't actually push the bar of password entropy up high enough that users will have a significantly difficult time remembering them. So when a user still creates a password like I'm a believer or 1024 Scott, it's much, much stronger than if they just created password or QWERTY, but it's not so strong that they have difficulty remembering it.
Next question.
Hey, Shouling from Georgia Tech. I actually have 2 questions. The first question is, can you talk a little bit more about the prediction rules of your meter or something? And the second question is, if the prediction logic is based on some fixed logic, can the adversary use this logic to design some new cracking algorithms which can avoid such kind of guesses? I mean,
Why don't you choose
thank
one
you.
of those two questions to answer so that we can save time for one more question?
Okay, so I'll take the more interesting question, I believe, which is, can an attacker sort of use the predictions made by Telepathwords to change how they make guesses? So they certainly could. So any kind of system that's a new password policy is going to induce a new probability distribution on resulting passwords. And if attackers understand that probability distribution, they can optimize their guesses for it. But what we have found in previous work is that as you discourage users away from common behaviors, they don't all immediately flock towards some other common behavior. They sort of spread out a little bit, not a lot, but they spread out a little bit over maybe a distribution of other behaviors. So it's our hope that even though Telepathwords, it might be in the future that attackers will get better at cracking Telepathwords-based passwords, they still won't be as good as they are at cracking passwords now.
Alex for DC Google. I'm wondering, why did you look at a pure dictionary-based policy without the 3-class requirement? And how did that compare? Did that compare as well as the 3-class with dictionary requirement?
No, so we actually did not test that. So we used 3 class 8 as our baseline condition. So basic 8 was more of just a control condition to see how bad it was. We weren't really expecting that 3 class 8 would be as bad as basic 8, so we weren't expecting that we would need to look into just adding a dictionary policy, but that's definitely something that would be good to look at in future work.
Let me ask one last question while our next speaker is setting up his slides. Can I download this and use it on my website, and if so, how?
I will let Stuart answer that question.
That's fine. All right, so Stuart, feel free to set up for your next talk. Let's thank the speaker again. Thank you.